All right, so part two. So part two is basically just examples for us to do. Okay. All right. Now here it says find the following limits using substitution. So uh, something I want to explain before we actually do this. I kind of talked about how we find a limit. This is a function, obviously. So I can graph this, okay, and find the limit that way. And we're actually going to do that in just a second on this following example. So remember that with all limits, you're actually finding where is this graph approaching? Where is this graph going as I approach a specific value? Now we can use substitution, which just basically means plug in the variable and it'll tell you where the graph is going. So this is going to seem extremely easy at first, okay? Honestly, it's not that hard, but there are some rules that go into it. All right, so first off, the limit as x approaches 5 of 10 minus 3x. I just take the function 10 minus 3x and I substitute in 5. Solve it, 10 minus 15. So the limit is negative 5. So if I was to graph this, basically I know that the graph as x is approaching 5, my y value on that graph is negative 5. Alright, so we're going to fly through these examples. Now the limit as x approaches negative 1 of this parabola, so I'm going to plug in negative 1, and I'm going to solve this, so 3 plus 6 minus 1, and that is going to give us our answer of 8. Okay? Now here, there is a rule for this, alright? And it tells you the limit as x approaches c of any a, if it's just a coefficient a, is a. Alright? Just think of this. Remember that this is a function. This is f of x is 5. So imagine yourself graphing that. If you graph this function, which is y equals 5, you know that it's going to look like this. 1, 2, 3, 4, 5. You go up to 5 on y and you draw your line. Correct? So as x approaches 3, where am I always? I'm on 5. So my answer here is just 5. Alright, so here the quotient, right? There's division, but of course there's no x's in the numerator, so it's not really going to do anything for me, but you just use substitution. So 4 divided by 5 minus 7 is 4 over negative 2, which is negative 2. Okay. Now here you can see that it's 0 from the positive side. But you're still just approaching 0. Okay. So as long as you're using substitution, you just have to substitute this in. Alright, now something does happen if the denominator ends up being 0, but we'll talk about that in a minute. So I'm just going to plug in 0. So 4 minus 0 over 3 plus 0 cubed, which is 4 over 3. And there's my limit. Now you can have limits of trig functions, but usually, your inputs, if you don't have a calculator, are going to be straight from the unit circle. So sine of pi over 3 times cosine of pi over 3. And of course, that is going to be square root of 3 over 2 times 1/2, which is square root of 3 over 4. Okay? Alright. Now this next example says find following limits graphically. So first off, we actually have to graph this. Now to graph it, let's pretend that you don't have a calculator. So step 1 is graph. So pretend you don't have a calculator. So I'm going to make an X and Y table. Now, I hope you guys remember that when you have a rational function, the 0 of the denominator, remember, tells you something extremely important about the graph. So what it tells you is that this graph has an asymptote at that 0. So I know that, so I'm going to graph my asymptote right now. Right at 3. So I know there's an asymptote right there. And if you remember that the zeros of the numerator give you an actual 0 on the graph. So I know that this graph has a 0, has an x-intercept right there. Okay, and let's just double check. So when I graph this, I want a few points in the negative side, I want a few points on this side of the asymptote, and then I want a few points on this side just so I can see where this graph is going. So we're going to go -2. I think -2 is more than enough because I know that it's going through 0. I just want to know, am I starting down here or am I starting up top? So -2. I already know what it's going to be at 0, but let's just prove it. So we're going to choose 0. I'm going to pick 1, and that should tell me where it's going, but of course you can pick more points. Now I know at 3 it's going to be undefined, but I'm going to show you that it's undefined. And then I'm going to pick a number after the asymptote, which is 4. And let's pick a bigger one. So I'm not going to go with 5. I'm going to go with 8, just so I can see where the graph is going. So I'm going to plug this in. So when you plug this in, when you plug in -2, so -2 over -5 is obviously 2/5. At 0, 0 over -3 is 0. At 1, 1 divided by -2, which is -1/2. At 3, it's going to be 3. And what happens here is 3 minus 3, which is 0. So 3 divided by 0 is undefined, which makes sense, right? That we have a vertical asymptote there. So at 4, 4 over 1, which is 4. At 8, it's going to be 8 over 5, so 1 and 3/5. Okay, and let's graph those points. So -2 is I'll just use it. So at -2 we have 2/5, about right there. I know I'm going through 0. At 1 I'm at -1/2, and I kind of can see, you know, this is a rational function, so I know that it's doing one of these. So here's one of my branches approaching the asymptote. Okay, and then I'm going to keep going. At 4, my graph is up at 4, so 1, 2, 3, 4. And then at 8, I probably should have picked 7, but whatever. At 8, I am at 1 and a little bit. So obviously it's kind of going down in this direction. Okay, so there's my graph. And now I'm going to find the limits. Now here the limits are, I have a right-sided limit. So it's asking, as x is approaching 3 from the right side, where is this graph going? So as I'm approaching 3 from the right side, where is this graph going? Up to positive infinity. As x is approaching 3 from the left side, so here's my left side of the graph, I'm going to follow this graph. Where is it going? To negative infinity. So what that means, remember our definition, because these two do not equal, so I know that my actual limit for this function as x approaches 3 does not exist. Okay? Alright, so moving on to limits of polynomials. So for any polynomial, for any polynomial f of x, and c is a real number, the limit as x approaches c of f of x is just f of c, which basically means plug in whatever your c is into the function. It's just substitution. It's just a fancy definition for something we're already doing. Okay? And then for rational functions, if f of x and g of x are polynomials divided, which makes them rational, and c is any real number, then the limit as x approaches c of f of x divided by g of x is equal to f of c over g of c. Keep in mind that g of c cannot equal 0, but if it does, here's our little note. And we'll talk about this because there's a difference between solving these problems algebraically and finding the limits graphically, and we'll talk about that in class. But when substitution leads to a 0 in the denominator, you factor and reduce and then find the limit of your reduction. So let's put that to practice. So here's our first example. Limit x approaches 2 of this rational function. So first I'm going to try to solve it by substitution. So I'm going to plug in 2. So 2 squared minus 7 times 2 plus 10 over 2 minus 2. So right away you notice what happens here. You end up with a 0. So I can't solve this the way that it is. So really what this is telling me is graphically there is no limit that exists as x approaches 2. But because it's asking us to find it algebraically, we factor. So let's factor the numerator. So the limit as x approaches 2, when you factor the numerator, you end up with x minus 2, x minus 5, divided by x minus 2. And you notice that these two divide out to equal 1, so they cancel each other out. And remember, from rational expressions, when factors cancel out, that means there's a hole there. Okay, so keep that in mind. So now my new function that I'm finding the limit for is x minus 5. So now I can use substitution. So I want to know as x approaches 2, so I just plug in 2 minus 5. And so algebraically, the limit is negative 3. But graphically, it does not exist. And we'll talk about that, why they do this in class tomorrow or the day after. Okay, the sandwich theorem, aka the squeeze theorem. Okay? So the squeeze theorem says if you know that a function has a set range, has a set y, like for example sine of x, we know that sine of x, its set range is from -1 to 1. We can use the sandwich theorem to solve this. So the definition looks a little funky. So I'm going to write this down. So if g of x is less than or equal to f of x, which is less than or equal to h of x, for some interval a, b, but x cannot equal c, then the limit as x approaches c of g of x, okay, so this one, is equal to the limit, then, I shouldn't have said then, and the limit as x approaches c of g of x is equal to the limit as x approaches c of h of x. So if the two functions on the outside are equal, if their limits are equal, then I can conclude that the limit as x approaches c of f of x is going to be the same as these. Okay? So if these two equal the same thing, let's call it L, then I can conclude that the main function that I'm dealing with is also equal to that same exact limit. So here's what we mean. So I'm going to first do this algebraically, and then I'm going to show you on the graph why it works out. So we know that sine of x, that this part of sine of x, has a range, has a set range, the interval between -1 and 1. So because I know that, I can break this up into 3 separate functions. Now you notice that I didn't combine the x in there, because as soon as, you know, sine of x divided by x, that's not its range. It's not -1 to 1. So I can break this up into a mini sandwich, and I can say the limit as x approaches infinity from -1 over x. So you notice I'm using the actual intervals, and I'm keeping the x from the denominator, is less than or equal to our actual limit, which is sine of x over x, and that is less than or equal to our outer interval, 1 over x. So what we have to do right now is we have to solve this one and this one. We have to find their limits, and if their limits are the same, then we can conclude what the limit of our actual question is. So I'm going to plug in infinity in for x. So -1 over infinity. So literally just think of it. If you plug into the calculator -1 divided by 1,000 or -1 divided by 1,000,000, you're going to get an extremely small number. It's going to be so close to 0 but not 0. But that's the whole point of limits. Where is it approaching? It's approaching 0. Correct? And now here, I'm also going to solve it. I'm going to plug in my infinity in for x. And I know that 1 divided by infinity is also equal to 0. So because these two equal each other, then I can conclude that the limit as x approaches infinity of sine of x over x is 0. Now if you graph this, and I apologize again, I graphed this on Desmos, okay? This graph does one of these. And I'm going to try my best to graph it, but I'll show you guys in class what it kind of does. But it does one of these. Okay, it starts going up and down, up and down, up and down, and then the waves get smaller and smaller this way, and then it does the same thing on the other side. So you notice that as x is approaching positive infinity, what's happening to the actual graph? It's getting so small that it's approaching 0. It's approaching the y value of 0. Alright? Alright, next up. Again, this is one that you can use the sandwich theorem. Now this is sine of 1 over x. And this also has a set range. The range of sine of 1 over x is between negative 1 and 1. So because it has a set interval, we can use the sandwich theorem, aka the squeeze theorem. So I'm going to break this apart. I'm going to basically replace this with the two intervals for the outside functions, but I'm going to leave this x squared in there, okay, because that's not part of my interval. So if the limit as x approaches 0 of x squared times negative 1 is less than or equal to, and I'm going to put my main function in here, x squared sine of 1 over x, and that is less than or equal to the limit of x to 0 of x squared times my outside interval, which is 1. So based on the sandwich theorem, if I solve these two and they equal each other, then that means I have my answer for that one. So x is approaching 0, so I'm going to use the substitution method, and I'm basically going to plug in 0 squared times negative 1, and of course that equals 0. And then here, 0 squared times 1, and of course that equals 0. So they both do equal each other. So guess what? The answer to my function is the limit as x approaches 0 of x squared times sine of 1 over x is 0. And again, when you graph this, and we'll look at it closer tomorrow in Desmos, you end up with a graph. When you graph this function right here, it looks like this. So you notice that as x is approaching 0 from both sides, where is this function going? It's approaching 0. Alright, so this was fun. Good night. See you guys tomorrow.